Hey everyone, today is the second video of Unit 3, and in the last video we were talking about work. So today we're going to talk about the opposite kind of work, which is energy. Energy is another one of those things that has a really strict definition in physics that is not always as strict outside of physics. We have a lot of things that we consider energy in our daily lives, but physics really is very specific about what energy is and how it works. Now, in my last video on work, I touched briefly on energy just in the context of what it is related to work. And if we remember, energy is the capacity to do work. So an object that has some energy has some capacity to do work. And that's really how energy is defined relative to work. And today we're going to look in a lot more detail at energy, at types of energy, at how energy relates to work, and at how we calculate energy. And that's really what the topic of this video is. So, in order to talk about energy, we need to talk about this thing called the work-energy theorem. And it's a really fancy name for a pretty simple concept. The work-energy theorem, let me spell that right, is basically this concept that says that when work is done on an object, the energy of the object changes. And this is a pretty intuitive concept given the definitions. Energy is the capacity for work. Work uses energy, or it changes energy. When work is done on an object, the energy changes. And that's literally what the work-energy theorem says. When work is done on an object, its energy changes. And we can say this quite specifically with an actual equation, which is what we do. And we say that work is equal to delta E. And what delta E is literally the change in energy. Delta means change, and E is, of course, what we use for energy. So work, because that's what W is equal to the change in energy. And another way of looking at the change of energy is just that it's the energy at the position or time 2 minus the energy initially. So it's the final energy minus the initial energy. And that's all that delta E means. Delta anything is always just the final minus the initial of that thing. Just like delta T is the final minus the initial, or any other delta you would see in physics. Delta E is the final energy minus the initial. And that is what work is. This work-energy theorem and the associated equation, this equation is very important, like super, super important. If you take one thing from this video, make it be this. Work is equal to delta E, change in energy. Now, there are a lot of different types of energy. There's lots of them. And the thing is, we're not really going to look at all of them because that would take forever and people dedicate their careers to this. There's some different types of energy that the physicists deal with are sound energy, thermal energy, electric energy, chemical energy. There's so many different ones. And some of these we'll get into later in the unit. But for now, we're going to focus on really only two types of energy. I'm going to start by talking about them really simply, and then we're going to go in depth into each of them. The first type of energy is what we say EK, which is kinetic energy. Kinetic energy. And the second type of energy we're going to deal with is EG, and that is gravitational potential energy. Sometimes you might just see gravitational energy. It's the same thing. Not everyone says the potential. Note this is a lowercase k. I know it doesn't really look like it. I'll try and make that a little clearer. So this is kinetic energy, gravitational potential energy. Those are the two types of energy we're focusing on here. And just as brief what they are, kinetic energy is basically the energy of things that move. We've been dealing a lot with things that move, balls and people and cars and all sorts of things. And these things have kinetic energy while they're moving. Gravitational potential energy, there's two parts to this. There's the gravitational part and there's the potential part. And I'm going to explain what potential means in a second. So for now, just gravitational energy is basically just the energy having to do with gravity. We've dealt with the force of gravity. Now we're dealing with the kind of gravitational energy. Okay, now let's talk about a very, very important thing, which is the difference between kinetic and potential energy. You'll find a lot of things that are kinetic or potential energies all the time. For instance, thermal energy is a type of kinetic energy, whereas gravitational potential is clearly a type of potential. So is elasticity. It's a type of potential. So all types of energy fall into either kinetic or potential. Now, the confusingly also named kinetic energy is a type of kinetic energy, and gravitational potential energy is a type of potential energy. So we're dealing with one of each of these types, but what do these types mean? Well, the simplest way to think about it is kinetic energies involve motion, whereas potential energies involve things which are staying in one place. And that's kind of an okay definition, but it misses some very important parts. So I'm going to explain the difference using an actual example. And that example is going to be this ramp and this rock. Yes, that's a rock. All right, so let's explain what I'm trying to do here. This rock has a couple different types of energy. Now, in theory, it has all sorts of energy. It has thermal energy. It has, kinetic energy, potential energy, and probably lots more. But for our point, we're going to talk just about kinetic and gravitational potential. And these are specific types of kinetic and potential energy. Now, the kinetic energy, what kinetic energy means is pretty straightforward. When this rock is moving and it's going down the hill, it's like, woo, I'm here now, and goes down again, it's like, now I'm here. That motion is dealing with kinetic energy. There's kinetic motion, the motion is happening, we have kinetic energy. So that's no problem, and that's probably the most straightforward thing to understand. But what is potential energy? So I'm going to erase this to explain. Potential energy is basically the energy of things that have the potential to move. Now, this is really not helpful, so let me try to explain that in more detail. This rock sitting at the top of this hill right now, if you saw this image, you'd think, well, of course the rock is rolling down the hill. That's what it's doing, Because there's nothing stopping this rock, of course it's going to be going down the hill. But if we just were like, nope, sorry, rock, you're staying there. This rock is now frozen in place at the top of the hill, and an external force, the force of this wall, is preventing the rock from doing what it wants to do, which is go down the hill. So it wants to do this kinetic energy, but it's not doing it, it's being held back, so what it has right now is a high level of gravitational potential energy. And that means that the force of gravity is being exerted on it, and this energy is the energy of basically what it could be doing, which it could be moving. And it has this energy that's waiting, all bottled up, and then you release the wall. And when you release the wall, the rock's going to start moving down. And as it moves down, it's going to convert this gravitational energy into kinetic energy. And it's going to convert it more and more and more and more and more until it hits the ground here, at which point it will have exhausted all its gravitational energy. Gravitational energy will be basically zero, and we'll just be dealing with all the kinetic energy it accumulated until it stopped there. And now it's done, it's gone, it has quote-unquote no energy. So we're going to deal with systems which are very similar to this quite a lot. Systems where an object has initially high gravitational potential energy, then they're released, that gravitational potential energy decreases and converts to kinetic energy over time, and then eventually we end the journey. Hopefully that's helpful to explain the difference between kinetic and potential energy. It'll become more clear as we do more examples. Now, what are kinetic and potential gravitational energy, which are the two specific types of energy we're dealing with? Well, let's start with kinetic. Kinetic energy, we keep talking about the energy of movement. And that's really what kinetic energy is, and it's one that we're going to be dealing with an awful lot. And kinetic energy has a formula for it, and we're going to look at this formula right here. This is the formula for kinetic energy, and we're going to be dealing with it quite a lot. You want to put this on an organizer or memorize it or something. So I'm just going to go basically variable by variable. This is the kinetic energy itself. This is obviously a half. And the two variables the kinetic energy depends on are the mass of the object and its velocity. And this makes sense. We're dealing with an object that's moving, and the energy is describing this motion. So what it cares about is how fast it's moving and how big or how much mass that thing that's moving is. And that's really what kinetic energy is. This formula, EK equals half mv squared. You're going to be using this a ton when you do kinetic energy. On the opposite side, we have obviously gravitational potential energy. Gravitational potential energy. And gravitational potential energy is, like we said, the energy of things that have gravity pushing on them, basically, but they're in place. They're getting ready to move because of that gravity, and it's the potential energy. That's kind of the important point here. The energy is potential. So gravitational potential energy has its own formula, and that formula looks like this. Right here, and sometimes you're going to see it like this, sometimes you're going to see it like this. The delta is not always there, don't worry about that. Let's just look at the simpler form here. So at its core, potential energy, gravitational potential energy, is equal to mgh, and these are three variables that are involved. The first one is again mass. The second one is acceleration due to gravity, and we've dealt with this variable a lot. And acceleration due to gravity, we all know, is equal to 9.8 meters per second squared down. And that's always going to be true in this equation unless we're on a different planet. And finally, we have h, and like I said, sometimes you'll see it as delta h. This is height. It's displacement. It's literally the same as displacement, but it's vertical. You're going to see that we use h instead of d a lot when we're dealing with vertical displacements, which are common in gravitational potential energy. So in my hill example, where the rock was here, it's this distance, this displacement, which we would call delta h, that would be put in this equation. We'd be dealing with that and the mass of this rock, and obviously 9.8 meters per second squared down. So these two equations, the equations for gravitational potential energy and for kinetic energy, are super, super important, and you should really make sure you know them. Gravitational potential and kinetic energy are going to be dealt with a lot, especially in the next video when we talk about the conservation of energy, which is an important law that will allow you to solve problems with energy, and I'll explain that. Finally, there's kind of two smaller topics that need to be talked about. One of them is net energy, and we deal with net of a lot of things in physics. We've dealt with net force, we dealt with net work in the last video. Now we have net energy, which is of course just E net. And net energy is exactly what you think. It's the total energy for a system. Now, I'm going to explain one thing about net energy, and that is that we're going to use it very rarely. And the reason we're going to use it very rarely is when we were doing a net work or net force, it was very easy to find all the forces, all the work being applied, and add them together to get net work, net force, no problem. Net energy is a lot harder to find because there's a lot of types of energy. Like I showed you two today, there's at least like 10 or 15 other types. And these types of energy are everywhere in everything. There's thermal energy, there's chemical energy, all these things that are very difficult to calculate and even less important to us. And you would need to account for every single one of them on every object in order to actually collect net energy. And because this is really just not practical, and physicists know it, what we actually tend to use is mechanical energy. And mechanical energy is an actual useful thing. It's actually a capital M. Mechanical energy. Mechanical energy is equal to kinetic energy plus gravitational potential energy. So these two types of energy we've just been talking about, and frankly, the two types that we're going to be dealing with most often in the couple next videos that are coming. So that, when you add them together, you get this mechanical energy. I'm going to write that out. Mechanical energy. And it's like a poor man's net energy. It's net energy, but ignoring a lot of different things and just focusing on these two things which affect the object's motion directly, the gravitational potential and the kinetic. And because we're mostly going to be dealing with this mechanical energy, we can conclude that, remember how work equals delta E? So the total work is equaling the total change in energy. Well, we can conclude that work is going to equal delta EK plus delta EG. And this would be the net work. And this is going to become very important because basically in these systems that we're analyzing in the next video with our law of conservation of energy, We're just going to be focusing on kinetic and gravitational and how they exchange. And that's really the focus. All right, let's zoom out and summarize what we've done. So we've talked about energy, what it is, and the work energy theorem, which says that work is just a change in energy right here. We've talked about the different types of energy, that is kinetic energy and gravitational potential being the two that we're going to look at. We've talked about the difference between kinetic and potential energy using this example. And then we've looked at the formula for kinetic energy over here and the formula for gravitational potential energy over here. These are very important. Also, what net energy is and why we usually don't care about it, why we like mechanical energy instead, which is the combination of kinetic and gravitational potential energy, and how that applies to our original work energy theorem, because net work is going to equal the delta kinetic energy and delta gravitational potential energy. That is all for this video. It was a kind of a shorter one-ish. And in the next video, we're going to go into something called the law of conservation of energy, which is going to explain how we can use all these facts to actually solve practical problems and analyze real systems. Thanks for watching.